All right, so today is the only lecture of the week. I hope we had a good long weekend.
Yes, we did, sir.
It will be a non-programming lecture today just to keep us even, so I'm sorry. No programming for the week, but you're working on an assignment. I'm sure that'll help cover that. But today I want to talk about logic a little bit more, and then an idea called framing, like a frame of reference. So, let us begin with two words that are very similar. They rhyme: deduction and induction. All right, so I guess first, before I define either of them, deduction is something that computers are awesome at, just like plug things in, discover truth or false, truthness or falsehood. And then induction is something that humans are much better at. I guess AI is getting better at this, but humans are good inductive reasoners, right? And so these two terms are going to help us actually answer this question. What makes an argument correct, for some definition of correct? I'll give you some definitions. A deductively correct argument, I guess. All right, so let's talk about deduction. That's easier to talk about, and it's very logical. It is as logical as you can get when you have an argument in logic. A deductive argument is pretty clear. All right, so just in general, when we're making an argument, no matter what kind, there are pieces of it that maybe we haven't heard terms for before. There's always something that you're trying to conclude. You're arguing that something is the case, right? You're being like, this is true, this is false, this is good, this is bad. You have a conclusion always in your argument, but you have some premises before those. Premises, however you want to pronounce it. Those come before your conclusion that kind of give it weight, all right? Those are just your assumptions. So premise just means assumption in this case. And so here is essentially your argument. Like you have a bunch of premises, P1, P2, little clouds of your thoughts, P3, and your conclusion, your goal, is to have something else be the case. Like I'm arguing that this is true based on these premises. That's how all arguments are deep down. Some premises, you're trying to use that as firepower to claim your conclusion. All right? Conclusion. So an argument is deductive when its conclusion is a certainty based on the premises. All right? The conclusion must always be true if this is a deductive argument. Always true. There's no room for ifs or buts. Always true. That's what it means to be a deductive argument. The premises imply the conclusion. That's another word we'll talk about. They lead to the conclusion. It's always true. It always has to be the case. All right, so here's an example deductive argument, and hopefully you'll see how the conclusion must follow from the premises. All right, so premise 1, it is sunny in Fresno. That's usually a true statement. It's true today. Premise 2, right, I'm making an argument right now. Premise 2, if it's sunny in Fresno, then Lawton won't be carrying an umbrella. All right, so those are my two premises, my firepower towards my conclusion. So I'm assuming those things, and then I'm using them to argue my conclusion. The conclusion is so, or therefore, Lawton won't be carrying an umbrella. Okay? That's the idea. So do you see how these two premises, if you assume them to be true, the conclusion must always be true. It's a fact, right? There's no getting around it. Like, all right, if you assume this, and then if you also assume that when it's sunny, I won't be carrying an umbrella, these two together must prove, right, that I won't be carrying an umbrella that day. Do we see how those are all coming together?
Yes.
It is always certain that if you assume those premises are true, the conclusion must also be true. That's a deductive argument. Okay? And so that's what computers are good at. They're like, does this work? Check. Does this work? Check. Does this apply? Cool. Therefore, I understand that the conclusion must be true. So computers are good at that kind of reasoning. Humans are better at induction. Induction is kind of the opposite. It's all about probabilities. So when you hear inductive, think probabilities. It doesn't always have to be true. Probabilities. Probabilities. I spelled that right, yes. All right, so an argument is inductive when the conclusion isn't a certainty from the premises. It's just really, really likely. All right. There's also something called mathematical induction if we are math majors or we've taken a fancy computer science class. This has nothing to do with that. It's an overloaded term. So induction, in this case, this is logical induction. We're talking about arguments. An argument is inductive when the conclusion is very likely based on its premises. All right. So here's an example inductive argument, and I hope you can see the difference between it and the one on the previous slide. So here's your assumption, your premise. Every time I've walked by that dog over there, it has not tried to bite me. So my conclusion based on that premise is that, okay, so or therefore, the next time I'm going to go walk by the dog, he's probably not going to try and bite me, right? You see how there's the word probably in there? That makes all the difference. Maybe if the dog's having a really bad day, or somebody provoked it, then he will start biting people. Hopefully not. But there is a possibility that your conclusion is false, even based on your premises, based on your evidence. Does that make sense? So that's the difference between induction. It's just all about probabilities. Like it's not a certainty that the conclusion will be true. It's just very likely based on your premises. And then deduction is conclusion is a certainty. It must be true. It always is going to follow from those premises when you have a deductive argument. All right. Any questions about the two? It is a bit vague still, I would say, but as long as you get the idea that induction is not always true, that's what I want you to know. Yeah. Yeah. Check some boxes. You can always prove your thing. That's what deduction is. Induction is sometimes, usually, words like that don't imply always. So maybe Kant's a big fan of deduction. I don't know. All right. With that in mind, let's describe arguments now. So you can say that an argument is deductive and inductive. I guess those are adjectives too. But you can also say that arguments are valid and sound. Those are some big useful words. All right. Soundness, by the way, is, before I get into these, soundness is stronger than validity. It's a bigger word anyway. Stronger than validity. So if you have an argument and somebody says it's sound, it's valid just because it's sound. To be sound, you must also be valid. Okay, so let's get into these, and this will help us attack arguments. So if you see somebody on Twitter or something saying something, you notice like, oh, this argument is invalid. Oh, this argument is not sound. That is good firepower. That's a great way to attack somebody's argument. All right, so let's learn what these words mean. All right, if you have an argument, and this will help us attack those arguments. If you have an argument, it's valid if it's impossible, absolutely impossible, this is about deduction again, if it's impossible for the premises to be true and the conclusion to be false. That's what it means for a valid argument to exist. If it's impossible for the premises to be true and the conclusion to be false. So under those assumptions, maybe they were weird, incorrect assumptions, the argument still is, it makes sense and it applies. All right? So if the conclusion follows from the premises, always, it's a valid argument, all right? You may have weird premises, though. So I'll get to that in a second. So that's validity. And then soundness is stronger than that. An argument is sound if it's valid, so it has to be valid first. And then also, the premises weren't weird. They were actually true statements to begin with, all right? So we're not like coming up with a hypothetical world where everything is beautiful. A sound argument is when it's valid and those premises are true. Okay, but it's valid if the premises imply the conclusion. The conclusion follows from those premises, even if they're weird premises, like they assume the Earth is a perfect sphere or something like that in a physics class. All right, so arguments are sound if they are valid and all the premises are true. So here are two examples that should help this make sense. All right, so this is like the argument that you learn about when you learn about validity and soundness in a philosophy class. So here it is. You got two premises, let's say 1 and 2, and they're being used as firepower towards this conclusion. So some people put a line here to separate the premises from the conclusion. I will do that. And here they are. So this is a sound argument. All men are mortal, first premise. Assume that. Socrates is a man. Assume that. 3, therefore, this is our conclusion based on the premises. Therefore, Socrates is mortal. Okay? So do you see how, first of all, it's valid because, well, all men are mortal, Socrates is a man. Plug him into that, you get that Socrates is mortal. Therefore, Socrates is mortal. So that follows. It's a valid argument. And then it's also sound because the premises are both true. So are all men mortal? Unless we've been lied to, I think that's true. And then is Socrates a man? I guess there's a debate on whether Socrates even existed, but let's trust Plato and assume that he really did. So those are two true statements, and so it's a sound argument. All right, do we see that? Do we also see why it's valid? Why the conclusion follows from the premises? All right. So yeah, there are no superheroes. So one is a true statement in theory. All right, so that's a sound argument. Let me show you a valid argument, but it is unsound. All right, so again, there's two premises and a conclusion based on them. I'll draw a line. Premise 1, everyone who watched the play called Hamilton enjoyed it. All right, that's one assumption. Assume that, and then assumption 2, assume that John watched Hamilton. We know him, and he watched Hamilton. And then here is a conclusion based on those two assumptions, those two premises. So, therefore, John enjoyed Hamilton. Do we see that this is a valid argument? If you take both of these and assume that they are true, then yeah, totally, the conclusion follows, because everyone who watched Hamilton enjoyed it. John watched Hamilton. We can plug him into this statement about everybody, and therefore we get out the fact that he enjoyed it. Does that make sense? We're assuming those things, just take them for granted. Then yes, the conclusion follows. So it's valid for sure, but it's not sound, right? Because some people don't like Hamilton. Yeah, that's the idea. They have bad taste, but they may not like it. All right, so this is why. Like, this one's true. Maybe John really did watch Hamilton, but if there is an X there, it does not work out. All right. But again, yeah, it's valid because, like, Socrates is a man. Plug it into that, you get the conclusion. It's valid. This one's valid because John watched Hamilton. Plug John into this statement, you get the conclusion. So validity works, but soundness does not. Okay? Any questions about that? So valid if the conclusion follows from the premises, and sound if it is valid first, and then all the premises must be true. So if we're happy with that, I have some questions for you to see if you can get it. I'll give you this definition on this first slide here. All right, so it's up there. Let's see here. I guess we'll do this one together, and then I'll give you a few to try. So let's keep this, though. All right, so is the following valid or sound? Here's our argument, and you've got two premises and a conclusion. I'll draw a line as usual. All right, so remember that it's not sound if you can find like a counterexample, so be on the lookout for those. So let's see if it's valid first, because if it's not valid, it's nothing, right? All right, so all birds can fly. First one, first premise. Assume that. Bats are birds. Assume that, all right? Does the conclusion follow?
No.
If you assume these, if you assume those without any extra thought, does the conclusion follow? I think it does, right? Assume bats are birds, plug them into all birds can fly, then yes, you can prove it is valid. The conclusion follows from those premises, yes? If you assume those things. Big if, right? So yes, it is valid. Do we see that? Even though those were weird premises. Just under those assumptions, yes, it follows. It works out. Is it sound, though? Yeah, it's not sound at all. Why not? Yeah, that's one thing. I had to look that up on Wikipedia. They are mammals. Bats are mammals, so that's not true. And then can all birds fly, too? Now we got penguins and I'm sure other things. Emus. So yeah, that's why it's valid, but it's not sound. All right, I'll put that over there. I'll steal this. The next slide. Any questions about that example? You see how we can apply those things? And you can bash this argument now because they're like, it's unsound. Why should I trust it? But it was valid. All right, now I have questions for you guys. So please get into your peer instruction groups. Do your attendance. I'll stop this after the first one. Please go to the by clicker page. And I'll start it. But take a little while. Say hello to each other. And here are your questions about this. Here's your first argument. So all cats are mammals. All dogs are mammals. Assume those things. Therefore, all cats are dogs. Tell me, is that valid? Is it sound? Is it both? Or is it neither? All right? So see if you can break it down, and here are the definitions right here, if you have forgotten them.
Okay, are we putting different groups? Or we put groups?
You can be in whatever group you want to be in.
Okay, so what do you guys think? So
I'll give you a few minutes.
Are all dogs mammals, or do you think all cats are mammals, all valid? Okay, it's neither. So I'll type it in. It's neither. Reason. All cats. Well, I'm typing it in, so that way I'm writing why it's neither. Okay.
Oh, is this just for your notes, maybe?
Yeah.
This is a bike question.
Okay, so why do you think it is? No, it doesn't make. I think you're right because like cats can't be dogs because cats meow and they can live 9 lives. Dogs don't live 9 lives, right? So that explains it. And plus, cats don't really scratch behind your ear.
Take another
You're
minute.
absolutely right. How about you? How about you? I agree.
All right, like 30 more seconds, and then we'll talk about it. So get something in there. Your best guess?
We'll have to go to I have to by clicker D. Yep, there we go.
All right. Let's take a look. Let's see what we're thinking. Ooh. One of us thinks E. So maybe none of the above. I don't know. But we are all agreeing that it was D, so nice. Okay, let's take a look at that. That is the answer. So tell me why. Tell me why somebody picked that one. Why was it neither? Any brave souls?
The
Sure,
reason
right.
why it was neither because like cats that cats are mammal and cats are dogs. That doesn't make sense because cats can't be dogs and dogs can't be cats.
That's true for soundness, right? That I guess the idea is when things don't make sense, sometimes that means soundness is off. But under those weird assumptions, does the conclusion follow from the combination of those premises? Is the question for validity, at least.
It does. They all are mammal, yes.
So this is a tricky one because are these premises true statements? Yeah, they're totally true by themselves, but you can't combine them, right? The idea if they're supposed to be used to combine, they're supposed to be combined together to like power this conclusion, and the conclusion does not at all follow from those premises. Does that make sense? Like how you're telling me nothing about cats being dogs? Like you told me about mammals. Like this last thing doesn't even involve the word mammal. So it's just a weird argument. It's not even valid. Do we see that? And so the second it's not valid, it cannot be sound. So you don't even have to think about that. But if it were somehow a valid argument, it would have been a sound one because these are true statements. Yes? But it wasn't valid to begin with. All right, so X, it was neither. All right? Slightly harder one. Oh, let's keep on bringing this definition here if you still need it. So here's another argument. Again, two premises and a conclusion. If someone was a philosopher, then they weren't a historian. It's a weird statement, but see if you can parse it. And then, second premise, assume that Socrates wasn't a historian. And the conclusion is, therefore, Socrates was a philosopher. All right, so there's some weird negations going on and things like that. Something, the word no or not is in there in weird ways. Is it valid? Does the conclusion follow from those premises? Does that make sense? And then also, are those true premises? So give that a try and discuss.
All right. What do you think? Think it would be valid soundly if someone was a philosopher, then they weren't a historian, or Socrates wasn't a historian. What do you think? Okay, I think valid in history because like I feel like if someone was a philosopher, then they weren't historians. If Socrates wasn't historian. I think that they do connect. I feel like these two do connect. These two sentences do connect because like weren't and wasn't. That gives us keywords that they do connect. So look for keywords that. So I think the keyword.
Take another minute or so to discuss, and then we'll talk about it.
It says that there's no active question to answer.
Oh, I'm sorry, did I not start it? My bad, I got ahead of myself. There you go, now you can respond.
Yes.
Sorry about that. Alright. Do they follow? I don't hear any more discussion, so maybe I think we're ready. Yeah, I think that's as many responses as I got before. Nice. So let's take a look. What are we thinking? Ooh, do we have a majority? Not quite. But we're thinking C, maybe. Next most populous option is D. So let's take a look. Is this a valid argument? And so this is a tricky one. This is why I gave it to you. All right. This is how I want you to look at this when you break down these things. So if someone was a philosopher, then they weren't a historian. So that's what that's claiming. It's like, you show me a philosopher, you show me a proof that somebody's a philosopher, and I'll show you a proof that they were not a historian. Remember that symbol? Not, negation, historian. You show me a proof that they were a philosopher, and I'll show you proof that they were not a historian. That's what that first statement is trying to say. And then we have this one. Socrates wasn't a historian. So we know that somebody was not a historian. It's kind of what it's saying there. And so the question is, for validity at least, is can you plug this into this and get out the fact that they were a philosopher? That's the question for validity. And some of us thought yes. This was kind of tricky, and the real answer is no. This is an invalid argument because of the direction of this arrow. I hope we see it now that I've written the arrow. It's like, you show me that somebody's a philosopher, yes, that means they're not a historian. But if you tell me that someone's not a historian, you're kind of like trying to go backwards along this idea. It's like, show me that they were a philosopher then? If you weren't a historian, maybe you were a computer scientist. See how that's not correct to go in that direction? So that's why it's not valid. You can't plug it in and get the conclusion. It doesn't work out. You're going the wrong way. You see that? It's very tricky. That's why I gave it to you. So it's not valid, which implies the answer really is D. Does that make sense? And technically, those are both true statements again. So if it was valid, it would have been sound. Socrates was a philosopher. He was not a historian. So that's true. And then this is technically true as well. If they were a philosopher, then they were not a historian. All right, but you can't go backwards like that because maybe they were, I don't know, an artist, something else. Doesn't mean that you're immediately a philosopher if you weren't a historian. Okay, so the fact that there's negation, the fact that like when you say if, it's like there's a direction implied. That's a little weird, and we'll get into that further today. But hopefully that makes at least a little bit of sense. I have one last question for us before I move on. All right. So here's my silly last argument. All computer scientists like to dance salsa. Let's assume that. At least I do. And then some men are computer scientists. And then the conclusion is, therefore, some men like to dance salsa. All right? See if that is valid, sound, both or neither. I'll give you one last minute and actually remember to start the question this time.
Let's look at it. All right, so all computer scientists like to salsa dance. Some men are computer scientists, some are neither. What do you guys think? So I think it's neither because it doesn't very connect very well. Like I think okay, valid is sound. But we have to pay attention because like it says all men like to scientists like to dance salsa. You have to be careful of keywords, you know.
And it says some men are computer science, and some men like to dance.
Okay, so you have to see right.
All right, did we? All right, I think we all responded. Remember to do your attendance if you did not do that yet. I will stop that in just a minute. But it looks like we're ready. Well, let's take a look. Ooh, all right. We are, again, not a majority. This is why we're asking these questions, so that you can do it well later. But we're thinking C, maybe. Let's take a look. All right. Does it follow for once? Let's see. Does the conclusion follow from the premises? So, all right. All computer scientists like to dance salsa. So this is kind of saying, there's an arrow relationship going on again, like the if on the previous slides. Like, you show me that somebody is a computer scientist, they like CSCI, that's their major or something, then I'll show you that they like to dance salsa, right? So there's an arrow going that way, CSCI to salsa. You give me a computer scientist, I'll give you the fact that they like salsa. Yes? That's the first one. That's what it's saying. And then this one's saying some men are computer scientists. So like dotted line. You give me some men. Then I'll say that they're a computer scientist. At least one of them. At least one man is a computer scientist in the world. That's what that's saying. And the argument is trying to be like, can you go from man to computer science to salsa? So, therefore, some men like to dance salsa. Can you connect to these like this? That's what validity is asking. Does it follow? And yeah, it really does follow for once. So yay. Do we see why? It's like, all right, some men are computer scientists. Awesome. So, all right, I know that there are some men who are computer scientists. And then I know that all computer scientists like to dance salsa. So at least the men who are computer scientists like to dance salsa. And that's still some men. You see that? Again, getting a little boggled down with, getting weighed down with English. But that's what that's trying to say. So do we see how that follows? Does it make enough sense? So it's totally valid. And now the question is it sound? Usually when you see the word all, probably not. So do all computer scientists like to dance salsa? Unfortunately not. So that is not true. Some men are computer scientists though, so that is a true statement. But because one of those premises is false, that means it cannot be sound. So A is the answer. Does that make sense to us? That's how you do it. Any questions about that before I move on to something else? And so these arrows are very tricky. They're tripping us up, especially on this slide. So we should talk about those. That's where I'm going next. The idea is implication and just the word if, trying to translate that into logic so that we don't ever have to use English again, all right? Because we know it's ambiguous. What does it mean when we say, like, if this is true, then this is true? What does that mean? So let's talk about all of that, all right? So, okay. Here's a sample statement similar to one we did before. So here's Dad. He says that he will give us $20 if we mow the lawn. All right? There's an if in that statement. So let's talk about the if. And so we're going to try to translate this if statement, this statement involving if, into logic. And so we want to know, like, when is the if true? When is it false? And remember that false is like when we feel like we got cheated, like when somebody lied to us. So, all right. So Dad's saying this. If you mow the lawn, it's kind of saying it backwards. If you mow the lawn, then I'll give you $20. That's kind of the order to it. And so remember that falsehood means that you were lied to. So that's how we're going to interpret that. All right. Under what conditions would we feel cheated if we didn't get $20? And Dad said this to us. When did he lie? All right. So here are all the different combinations of mowing the lawn and then getting $20. All right. Here they all are. And now we need to decide, do we feel cheated under any of these circumstances? Here is every possible option. And we'll come back to the second. So, like, if we mowed the lawn and we got $20, we do not feel cheated, right? We did not get lied to because we got the money after doing the work. All right, so that should be true in that case. The if should have been true. What about this one? If we didn't mow the lawn, but we got $20 anyway, then Dad's statement still is true. Let's consider it to be true because, like, we did nothing and we still got money because Dad likes us. Okay, so that's fine. We don't feel cheated in that case. And same for this last one. If we didn't mow the lawn, but we didn't get $20, then we still don't feel cheated because we didn't uphold our end of the bargain, right? We didn't actually do the work. The only case in which we would feel cheated is this one right here. If we did mow the lawn, but we did not get $20. You see that? Because that would be us upholding our end of the bargain and then Dad not giving us what he said he would give us. Okay? So that's the one case this if would be false. You see that? That's how we're going to make this happen. We're going to make a new logical symbol, and it's going to be called implication, and it's going to stand for the idea of, like, if A is true, then B must also be true. All right? So add is true to all of these. Then B is true. And the logical symbol for implication is an arrow. Usually it's a double arrow, double-lined arrow. And it's like you put the thing on the if side on the left and the thing on the then side on the right. So like if this is true, then this is true on this right side. Okay? So it's called implication. It's the logical thing that means we're talking about if. All right? In programming, we call these conditionals. It's like our if-else kind of thing. So we just noticed its truth table, and here it is. So like here is the A and the B. So A is the thing like it's your mowed lawn, it's your premise. If you did this, and B is like your got $20. It's your conclusion. And then this statement is like if A then B. If A is true, then B is true. That's what you're claiming. And it's a true statement as long as you didn't lie to somebody. All right? As long as you upheld your end of the bargain. So as long as you can prove that you're not in this one, it was a true statement to say like, yes, if you do this, then I'll do that. If A, then B. A implies B. Right? So when we're trying to prove things, right, usually we're trying to say like, yes, this A implies B, this if statement in logic is true. When we want to prove something, we just have to say, we have to make sure we're in one of the rows that ends up with true in the truth table. So if we're trying to prove an implication, for example, we just have to show that we're in one of these and we're not in the bad one. We have to show that we could never be here. We could never have A true and B false, and then also, because that would put us here, right? A can never be true and B cannot be false, not at the same time, because that would put us in the bad case. Then it would not be true. Okay? So that's a little weird still, I think. Hopefully it makes a little bit of sense, at least in terms of mowing a lawn. But that's implication. It's a new symbol. We're getting rid of English for the word if, and that's going to be very helpful. Okay? So here is hopefully going to tie it all together. Let's talk about deduction because it has to do with implication secretly. All right? So these ideas again. So all men are mortal. That's like, all right, you translate that to logic. It's like if man, then mortal. That's what that's saying. Yeah? And then Socrates is a man. It's like saying that you know that man is true. So you're assuming these two things. Like if, this is your A and this is your B. If man, then mortal. That's what this is trying to prove, right? It's proving that Socrates is mortal. Therefore mortal. This is what the statement is trying to say. If this is true, assume that's true, assume this is true, then this also must be true at the bottom there. So that's what it's trying to do. And so deduction, the reason deduction works and it seems logical to our minds is that the conclusion really does follow like from the truth table for implication. Let me show that to you. The conclusion follows from the truth table for implication. Watch. So assume if A, or like these are our assumptions, right? Assume that this is true. Man implies mortal. So let's go back to this. Assume that we're in one of these three cases, 1, 2, and 3, because it's supposed to be true. We can't be in the other one. Then assume that man is true. That's the A. Assume A is true. That actually only leaves us with this case. A is only true, and the other one's true in this one case right here. And do you see how that tells us our conclusion must be true? Because, all right, if we're in that one row, was the B part true? Because that's what we're trying to conclude. Yeah, it totally was. Look at it. There it is. We must be in this row based on those ideas, and our B, which was what we were trying to conclude, really was true. That's, again, maybe a little too high level and hand-wavy, but that's the reason deduction seems right to us. Any questions about that, how I translated that? I'll admit it's a little weird. It took me a while to understand this idea, this truth table concept, for implication especially. But once you have it, once you do understand it, then like everything works out better because you can just start using logic rather than English. And then also you can make a computer that does this stuff, right? So can you draw a circuit diagram for implication? How would you make this output with A and B as inputs? Do you remember our circuits? It just so happens that, remember that you can make anything out of and or and not, or some other things. This one, A implies B, it's actually equivalent to not A ORed with B, surprisingly. And so you can make a circuit for this. Watch. It does work. Because what's not A? False here, ORed with B. If it's true, okay, that's true. not A, false, ORed with B, which is false. False ORed with false. That's the only way to make false. See how they are agreeing? And then the negation of A is true, ORed with true again, still true. And then finally, the negation of A is true, ORed with false. It was still true on the left, so true. See how they are equivalent? And so you can totally make a circuit that deduces things. Feed in A and B, have some like NOT gates and an OR gate, and then your output becomes A implies B. How cool is that? Make a computer do logic for you so that you don't have to do it. All right. I have just a few more topics. The first one, I thought it was funny because I spelled it wrong the first time. It's really called framing, but I typed farming the first time. So I just wanted to keep that for posterity's sake. But the topic is called framing. I just have one slide on it. It's just in the spirit of discussion and arguments. Not very relevant to the previous stuff. It's more like inductive stuff. It's more like you're in the heat of the moment and like somebody can't see your point. You're just so unsure why they can't see your side, your point of view. It's just so obvious what I'm trying to argue is correct. Even if like I'm giving valid arguments, I'm giving sound arguments, why can't they understand me? And so I assume you have an idea about this, but let's just spell it out. Everybody is living within their own frame, we say. That's short for frame of reference. And that's how they're going to view a situation or an argument that's placed in front of them. All right? So your frame, the frame that you are working in as a human, it shapes how you're going to look at things, how you view the world, and it's also going to shape all the assumptions that you're willing to make. So a sound argument to one person might just be a valid argument to somebody else, because somebody might not be willing to say that, yes, that is a true assumption, which is interesting. So, yeah, that's the idea. Other words for this is like your worldview. Your worldview changes how you view things, of course. What you agree with, worldview. And then it also has to do with like the connotations behind every word that is being used in this argument that you're having. Connotation. So, yeah, that's the idea. And so if you can control the frame of reference of your opponent when you're arguing with them, then you have the utmost power over them. You can control that argument as much as you would like, which is worrisome. So this is why I'm telling you about it. Watch out for people trying to control your frame of reference. And this is also the reason why somebody can think the exact opposite as you and even like give justification for it. Okay, so here are some different frames that come up a lot in politics. Again, very simplified. But if you just read this table, left wing, right wing stuff, this is what people traditionally who associate with the left side of politics and the right side of politics, these are the same things that these are the same ideas. They're giving them two separate terms. And do you see how those terms can influence the way that you would argue things? Which is unfortunate. And that's why it's hard for people to come to agreement sometimes. But this is why some arguments, even though you're making a good one, somebody else doesn't understand it. Because you might have differing worldviews, you might be living in different frames of reference, right? So that's, I think that's all I wanted to say about that. So that's another way that an argument could be propped up, or it might fail if you're in a different frame of reference. All right. Are we good to move on to the one last topic of the day? Let's do it. So this is more computational again, my forte. It's called state machines. It's really cute. It's a fun model of computation. It's very easy to think about. I think I can get you to believe the same. And it has to do with you're writing an algorithm, right? So it has to do with algorithms. It's a very easy way to make an algorithm. Algorithms. And it will answer this question. How can you break down the process of computation into logical things? It still has to tie back to logic, of course. It's like first do this, then do this. That's what we're doing in Scratch, right? Then do this. And then we have our output. It's kind of similar to an argument, right? I need all these things. I need all these premises before I have my conclusion. That's kind of how programs work, too. So it all comes back to computer science one way or another, I guess, in a computer science class at least. But here's a state machine. What they do is there's just a bunch of circles and arrows. That's pretty much all of upper division computer science, honestly. And what they do is they abstract over processes. At least these do, right? So the idea is that every circle, or I guess rounded rectangle over here, is a state that you could be in inside of your program or as a human or something. You're just modeling some process. It's very vague, so it can apply to anything. And then you can move around with these arrows that take you in between states, and those are called transitions, and they change your state. All right. So here's like a model of a very boring human up here in this top left. Let's say that the only states you could be as a human is at work, at home, and then in bed. Okay? Let's say there's a concept of a starting state as well. When you like start your program, you start your model. And so let's say that like you're born at home or something. So that's your first state. Just an arrow coming in means your starting state. And then so if you're at home, you can move around between states by following these transitions. So maybe it's like maybe you just woke up and you have to go to work now. You can go to the work state by taking the train. See, that's the only way you can get there. That's how you follow that. And so now you're sitting in the work state. You can do your work, whatever that state involves. And then the only place that you can go is back home. You have to take the train again to get back to the home state. So this is kind of limiting what you can do, but that's a very powerful thing inside of a computer, right? As a program, it's making sure that you can only do this one thing in this one special way, which is a good thing, at least to us. It helps us from having bugs. And so now you're back in the home state. Maybe it's bedtime. And so if you want to move from the home state to the bed state, you have to take the transition that is called sleep. That's the only way you can get into the bed state. And then you wake up, and then you're in the home state again if you follow that transition. But do you see how you can move around? You're kind of limited how you can move around. Like you can go to work. Maybe you go home for lunch. You can come back to work, take the train again. You can follow these a bunch of times if you need to. Maybe it's the weekend, so you stay home twice and go to bed twice, and then you go to work. But notice that you cannot go straight from work to bed. That's one thing that is disallowed by this model, by the state machine. And that's a very powerful concept. The things that you can do are just as cool as the things that you can't do. So that's state machines. Does that first one make sense? Pretty simple. And then here's kind of how you would actually use this to your advantage when you're writing a complicated app or something. And so here's like a model of a ride-sharing app like Lyft or Uber. Here's how they might program that deep down so that they make sure certain things happen in certain orders. So here's here's your start state. That's what that, I guess, circle is trying to represent. So you're on Uber and you want to buy a ride to somewhere, and so you request a trip. That's the very first thing that you do. And so you start out as a user in the trip requested state, and then the very first thing it tries to do is move you to the payment state. Right? It tries to charge your credit card before it actually gives you a ride. That's very important when you're programming this. You don't want to give people free rides. So then you move to the payment state, and hopefully it succeeded, but if it failed, you have to go back and request a new trip. Put in your credit card again or something. Only if the payment succeeds does a driver get assigned to you. Do you see how powerful this can be when you're implementing something? If you can translate this to code, you can guarantee that you cannot go from a trip requested state straight to like a driver assigned state and give somebody a free ride. You can prove that could never happen as long as you're implementing your program like this. That's a very powerful concept. I hope you can see that. And then like the driver's assigned, you have your little trip, and then the trip is complete. The driver goes into an unassigned state, and then I guess you could cancel. I don't know what they're trying to do here, but if you cancel again, that also puts the driver unassigned again. And then you go to like the end state where it asks you like to rate the people or whatever. And so that's kind of how you could model the way that a program works and the order in which you must do things, because you can't like go straight from here to here or something like that. Or from trip requested to driver assigned without going through payment. You can prove, if you implement it like this, that you must have gone through the payment state, which is very important, I'm sure, for somebody who's trying to make money off of their app. Any questions about that? That's why state machines are cool. You can prove properties of your programs very easily. You can see, like, just in a graphical format, that one thing could not possibly happen if you stuck to that. Right? So yeah, it's all about grouping your program into states and actions for those states. All right. So let me put you into a state machine as a student. All right. So let me give you a simplified state machine. So as a student, let's say that I think of you as having two states. You have a learn state and a practice state. All right. So again, like you walk into the class, there's nothing to do yet. I haven't assigned anything. So you start out in the learn state. That's your initial state. There's a concept of initial state. So that's like the arrow coming in. And then you're going to like move around between states when I have a lecture or I post things. Like as long as the lecture's not finished, you can have a transition that keeps you in the same state. It's fine. As long as the lecture's not finished, you keep learning, right? That's what you're doing now. And then the second I assign something and class ends, then you go to the assignment assigned state, and or you follow that transition, sorry, and then you go to the practice state. Now it's time for you to work on the assignment as long as that's not done. So you keep on staying in the practice state, follow that transition. All that assignment's not done, and then once it's lecture time again, you follow the transition back to the learn state. So that lets you move around. That's, I guess, how I imagine you as a student, maybe. And so that's how you can move around, and that's how I could model you, I guess. Make a state machine for you as a student in this class. And then there's also a concept of a final state, just like there's an initial state, and we draw final states with 2 circles. Like practice is a final state. That's the state that I want you to end up in as you're running this state machine on yourself. Okay? So your final state will be the practice state, because at the end of the semester you have nothing left to learn, so you won't be in the learn state. You'll be doing the final exam, and that's the last thing you do. You'll be in the practice state, and then your program, I guess, your model would end after you walk out, after completing the final. So that's the state you would end up in. Does that make enough sense? That is a state machine that might describe you. So this would be a final state. Final state. And so there's concepts of that too. Like I want to end up here. That's my goal, right? So let's take this back to programming. I won't make an actual program for this. It's a little too complicated, but it will make sense with the state machine. And this is actually the first, when I was in a computer science class at Fresno State, my very first one, the professor taught us state machines, and they gave this example. So I'm going to pass that example on to you now. All right? Here's useful work being done with the state machine that would have been very complicated to do otherwise. All right? So here's an algorithm for counting all the words in a sentence. We're going to use a state machine to do it. Right? So let's say that we asked the user in Scratch to type in a sentence that we want to count all the words in. So like in our answer variable, we get a big long sentence. And we want to give back how many words were in that sentence. Right? And I claim that this is a non-trivial problem, because what if the user, like maybe you might think, like, let's just count all the spaces. That will tell us how many words, or we'd be off by 1, count all the spaces and add 1. That's how many words were in the sentence. But what if the user was malicious? What if they gave, like, their answer was space, 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 right? Hi, mom, or something, space, mom. And so now you're counting exclamation point space. So what if that's the words or the sentence that the user typed? Or those underscore things were the spaces. So now you can't count spaces and have it work. You'd be thinking like, oh, there were 6 words when there's only 2. You see that? So it's a non-trivial problem. You can't just count spaces, but what could you do? You could use a state machine. So here is the algorithm. Let me show it to you. What we're first going to do is we're going to read every character. We're going to read every character, and that's what's going to drive the state machine. We're going to read every character in the sentence that we got from the user from left to right. And each character is going to drive the state machine depending on the character that we see. We will follow a specific either space transition or non-space transition. And so the key idea here that's going to inform our state machine that I'm about to show you is that white space, which is just any space character, like a tab, like pressing enter, or just a normal space, white space separates words, right? You can have multiple, that's fine. Each character, though, each character that you see that's not white space is either part of an old word, like the I is part of the hi. We saw that H first. It's either part of an old word that you've already seen, you already started looking at, or the start of a new one. See how that H, like it came after some spaces. That marks a brand new word. We should count that. That's what we can do with a state machine very easily. Right? So it is a 2-state machine that we need to count all the words in a sentence. And here are the states that we could be in. There is the outside a word state. We can be outside of a word that we're looking at, outside a word, or it could be inside a word. We're working through a word because we're reading a character at a time. We're inside of a word right now. So those are the 2 states that we could be in. And initially, we haven't read anything. We haven't looked at the first character, so we start out outside a word. We haven't seen anything yet. We're not sitting inside a word yet, for sure. At the beginning, that's our initial state. And so here's how you transition. Here are all the transitions that take you between states. So, all right. You suddenly become inside a word. If you were outside, you can move to inside when you first see a non-space character. Like you were outside a word here, but the second you see an H, you're now inside of a new word now. You found a brand new one. So you can move to that state when you see a non-space character. All right, and then you can remain inside of a word as long as you keep seeing non-space characters. Like the H brought us here, but then the I is keeping us here because you're still inside that same high word. So if you see a non-space again, you're still there. See non-space. But like, okay, sure, you saw the I, and then you see the space to separate words. If you see a white space character, that means you are now outside of a word again. There might be a million spaces after that first word, but you're not in one anymore. So do you see how you can move from inside of a word to outside of a word when you see a space? That could be your transition. And then you remain outside of a word, like if you see a bunch of spaces, you're still outside of any word. You haven't seen any real characters yet. So as long as you see space characters, you remain in the outside of a word state. Okay? And you see how you could transition as you read things. You could be like, all right, I see a space. That's going to move me. I start outside a word. Now I'm inside a word. Or sorry, I'm still outside a word because I just saw a space character. And then I see another space, still outside a word. See another space, still outside a word. See a non-space character. Now I'm inside a word. See the I. I'm still inside a word. I hope you kind of see that working. The trick is noticing, well, first of all, we have to keep a count of like all the words we've seen started at 0. And the idea is the magic happens where you have a transition and you notice that you were just now in a brand new word. All right? So we can increment our count when we follow a very special transition. Does anybody see it? Which transition, like which one of these, when we follow that, did we just see a brand new word and we should count it? Because that's going to be the magical part. Does anybody see it? It's a little subtle. But it is going to be this one. The second we were outside a word and we just found a new one, where we plop ourselves inside of a word in that state, the second we do that, we should add one. All right? And so now let me walk you through what's going to happen as we do all this. So let me make an arrow that I can just keep on reusing. And so I'm going to read every character one at a time, starting in the outside of a word state. I'll keep this to mark where I am right now. So this is the state I am currently in. Let's see if I can keep that separate. So I have this one. Cool. So I'm outside a word right now, and I just saw a space character. So I see a space character. I remain in the outside of word state. All right? I haven't seen anything real yet. See another space character. I follow the see a space transition. There's no way. Can't follow this one because I did not see a non-space character. So I'm still outside of any word. See? Space. Still outside of a word. Still run that. Stay in the same state. But now I see an H. Ooh. I can't follow this transition anymore because I did not see a space. I saw a non-space character, and so that moves me from here to inside of a word. Ooh. And I should add one if I ever follow that transition because I just saw a brand new word. That's the high. Does that make sense? And this, if you see it through, it will count the correct number of words. Then you see the I. It's like, oh, okay, I'm still seeing on space. I'm still inside of a word. Inside of the same word. It's not a new one. That I did not make a new word because I didn't transition from here to here. Okay? And then I see a space, so I follow my transition from inside a word to outside, because I have to, if I see a space, I must go down this arrow. Is that making any sense at all? And now I'm back waiting for a new word to see. Now I'm outside of anything. I'm ready to add again. If I see a non-space character, and there's my M, oh man, now I can be back inside of a word, and now my count's 2. See that? This is counting words correctly, and it will stay inside of a word as long as it keeps seeing non-space. Still non-space, 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 exclamation point, non-space. We're still inside of a word. And then our last character that we see is a space character. So we can't follow the C non-space transition and stay here. We have to follow the C a space transition, and we end up outside of a word. And that's just it. And then we're done. We've seen everything. And our count is the correct count of all of the words in that sentence, regardless of if the user was trying to be like nefarious and give us a bunch of spaces at once. Because we didn't care about spaces. We cared about the separation between spaces and actual non-space characters. And it kind of just falls out of the state machine what to do. If you ever follow this transition, add 1 to your count, implement this state machine as a program, and you've successfully counted the words inside of your sentence. So this is like what Google Docs is doing. They're running this code secretly. Microsoft Word is doing when you're trying to count words. Any questions about that? So this is a good example, I think, of the power of a state machine. It just simplifies an algorithm, I think. If you could implement this in code, then you could correctly have the count of words. All right. So that's exciting to me, at least. That was fun. So I think that's all that I want to do. Let me stop this before I forget. And then, is there anything left? No, because it's a short week, I guess I have nothing new to assign. Just keep on doing the things that are already out. And so the rest of the time is for you to work on things and ask questions. And I think that's all I got.